In this video, I'll talk about the rate law. The rate law tells us how the reaction rate depends on the concentrations of the reactants. For example, when A and B react with each other, the reaction rate is proportional to the concentrations of A and B. The equation is simple: R equals K times A times B. R is the reaction rate, K is the rate constant, A and B are the concentrations. Although A is called the rate constant, it's not really a constant. K depends on the reaction temperature. K is larger at a higher temperature, K is smaller at a lower temperature. K is called rate constant only because K does not depend on the concentrations of the reactants. Now let's look at these two pictures. Again, these two pictures show you that if we have more A molecules and B molecules within the same volume, there will be more collisions between A and B. And when you have more collisions, the reaction rate is higher. So again, the reaction rate is proportional to the concentration of A and the concentration of B. When we have this equation, R equals K times A times B, we say the reaction rate is first order with respect to A, and also first order with respect to B. And overall, it's a second order reaction. Why is that? This is because R is really K times A to the power of 1 times B to the power of 1. So if you look at this number 1, that means R is proportional to A to the power of 1. That means it's first order with respect to A. Similarly, it's first order with respect to B. And we can sum up the orders. And overall, we have a 1 plus 1. That's a second order reaction. Again, this K does not depend on A or B. Therefore, K is called the rate constant. Now let's look at a slightly different reaction. We still have two reactants, but this time it's NO2 reacts with NO2. Two NO2 molecules collide and they react. In this case, the reaction rate constant, K times NO2 squared, gives us the reaction rate. So in this case, this reaction is second order with respect to NO2, and overall, it's also second order. Now let's look at a simpler reaction. Let's say we have only one reactant, that's just A. A becomes the products, and then the reaction rate is equal to K times A to the power 1. Okay, this K can be very different from this K. We're just using the same notation here. Now we say this reaction is first order with respect to A because this is A to the power of 1. And overall, the reaction is first order. The rates of some reactions, not many, but there are some reactions, their reaction rates do not depend on the concentration of the reactants, or the concentration of the reactants never change. In this case, R is proportional to the reactant to the power of 0. So really, R is equal to K. The reaction rate is equal to the reaction rate constant. Again, you can say, well, it's reaction rate constant times the concentration of the reactant to the power of 0. But again, anything to the power of 0 is 1. Therefore, R is equal to K. In this case, this reaction is 0th order. For example, the electrolysis of water is a 0th order reaction because in this reaction, water, pure water, decomposes into hydrogen and oxygen. And throughout this reaction, the concentration of this pure liquid water never changes. Why? If you have 1 liter of water, it weighs 1,000 grams, that's 55.5 moles of water. So the concentration is 55.5 molar. What if you change the volume of water from 1 liter to 0.1 liter? Well, the number of moles also changes from 55.5 to 5.55. So both the moles and the volume change at the same pace. Therefore, the concentration of water remains 55.5 molar. So even this reaction consumes water, the concentration of water never changes. And this is a 0th order reaction. So now let's work on one practice problem. What are the commonly used units for R and K? So in this video, we talked about the unit of R. It's just molar per second. That's the change of the concentration of the reactants or the product per second. What about the unit of K? It depends on the order of the reaction. And we will determine the unit of K using the so-called dimensional analysis. So first, the reaction rate is always in molar per second. All right, and then let's look at the 0th order reaction. So R equals K. So when you see this equation, you know the unit of K is equal to the unit of R. So the unit of K is also molar per second. What about first order reactions? For first order reactions, R equals K times A to the power 1. Thus, first order. And then let's do some dimensional analysis. That means we need to balance the units. On the left-hand side, you have molar per second. Therefore, K times the concentration of A, that means K times molar is equal to molar per second. Therefore, the unit of K is simply second to the power negative 1. What about second order reaction? Well, we can just write out this equation, assuming A and B react, and the rate is first order with respect to A, and also first order with respect to B. Therefore, overall, this is a second order reaction. Let's balance the units. On the left-hand side, the unit is molar per second. On the right-hand side, it's the unit of K times molar squared. Therefore, the unit of K is molar per second divided by molar squared. The unit of K is molar to the power negative 1 times second to the power negative 1. How about third order reactions? Well, we can just write out this equation, and again, the unit of K is the unit of R divided by molar to the power of 3. Therefore, the unit of K is molar to the power negative 2 times second to the power negative 1. A couple more practice problems. What if we have a weird expression of the reaction rate constant? Let's say R equals K times A to the power of 0.5 times B. And what's the unit of K? Well, first, this reaction is 0.5 order with respect to A and first order with respect to B. Overall, it's 1.5 order. And then let's do dimensional analysis. The unit of K is the unit of R, which is always molar per second, divided by, over here, molar to the power of 1.5. And then the result is this. The unit of K, so that's the question mark here, times molar to the power of 1.5 is equal to the unit of R, which is molar per second, and then the unit of K, again this is the question mark, is equal to molar to the power of negative 0.5 per second. Another practice problem. What if A is equal to K times A times B times C times D? What's the unit of K? Well, this is simple. Again, on the left-hand side, the unit is molar per second. Therefore, the right-hand side must also be in molar per second. Therefore, K times molar to the power of 4 is molar per second. And then the unit of K, denoted by this question mark, is molar to the power of negative 3 per second.